Okay, I think we are recording. Yep. And this is the next video on indirect addressing. This is COSC 2325. And Ms. Serrano-Correa. And I hope that you've been entering all these examples. Please don't hesitate to email me if you have any questions. I'll be happy to work with you on this. So indirect addressing, we have indirect operands. We're going to look at array sum example, index, operators, and pointers. So we're going to look at how arrays work with assembly language. And what we're looking at today is how arrays work in other languages like C++ and Java, but we don't typically get to do all this. High-level languages will do a lot of this for us. But it kind of helps you understand how arrays work a little bit better in other languages. Okay, so an indirect operand holds the address of a variable, usually an array or string. It can be dereferenced just like a pointer. So I actually want to use the whiteboard for some of this today. Hopefully this will work, just because it's easier when I show it on the whiteboard. So when we're talking about an address, I can have something like this. So this is an array, and the array example that we have is called val1. So this is array val. That's the name of the array. How well you can see that. Super good. Let's see. So this array that you see on your screen has 3 elements, 10, 20, 30, and they're hexadecimal numbers. So this val1 has an address, and that address is also what we call the offset. So let's say that val1, so val1 actually has this address. So this first element begins at FFE0. If val1, if this is a byte array, and this is at FFE1, and this is FFE2, because this is 1 byte array, and the 30 is 2 bytes array. This takes 1 byte size, 1 byte size, 1 byte size. So anytime I use the word val1, right, when I type address of val1, it gives me FFE0, but really val1 by itself, like that, has FFE0 in it because it's an array. So val1 actually has the address of where the first element begins. To get to the second address in C++, we put a 1 right here. That gets us to the 20. This is val0, this is val1. This is val3. So what's happening in C++ is that, let me make this bigger. I don't know how it's going to look on your video, but what happens in C++ is it takes the 1 and it multiplies it times the size. So the size is 1, it says 1 times 1 is 1, and it adds it to the address. FFE0 plus 1 equals 1. If this was 2 bytes, then it would multiply 1 times 2 is 2, adds a 2 to the 0, and it gets to the next byte. So in here, we have offset val1. That means that we're getting the address of where this first byte lives, right? We're getting the address of this array. And we're moving that address to ESI. then here, what's happening is that ESI has the address of where val1 lives. So when you take, and I don't know if you can, hopefully you can see my pointer when I do this. I'm going to see, I don't think you can. Maybe now you can. When, so val1, sorry, ESI holds the address of val1. So both of these have the same addresses. They're both pointing to the same place. And I want to show you what that looks like. So here's val1. Okay. And val1, let's say that it lives at F, just to make this short, I'm just going to say F00. This is the offset that it lives. This is the address. ESI now, ESI has the same address now. So ESI points to val1 because it has FF0 or FF00. Or actually that's FF with 3 zeros, sorry. 00. So these two guys have the same address. So ESI points to val1. And remember, val1 has 10, 20, and 30. So when we say ESI, I think I'm going to put it like this. So 10 is here, is at FF00. 20 is at FF001, and 30 is just 1 byte away, F002. So when you say ESI, you're pointing to the 10. So the 10 gets moved to AL. When you increase ESI, you're increasing it by 1. So you're increasing the address. So if the address F000 in ESI, then you add 1, and now you're pointing to this location, which is 02. So here we increase it by 1, we get to 20H. We increase it one more time, and we get to the next value, which is 30H. So here what you're doing is you're adding to the address because ESI contains the address. So you're adding to the address and then you're moving the value into AL. When we say offset, we mean give me the value that ESI points to. Don't give me the address, just give me the value. So by putting these square brackets, that's what we're doing. We're dereferencing, we're getting the value that lives in ESI, which is the 10, 20, 30, and not getting the address. Okay. Clear all drawings. And mouse. Give me just a second. Let me save something here. I don't know any folder. Okay. All right. So use pointer to clarify the size attribute of a memory operand. So right here we have my count, which is word size. So this is 2 bytes. Give me just a second. I'm going to write in here again. So this is 2 bytes. Red. Okay, so this is word size, so that's 2 bytes. Here we're saying offset my count. So give me the address of where my count lives. So this gives the address and it moves the address into ESI. Let's just say that the address of my count is FFE0, just like we've been doing before. Then here it says increase. We're not increasing ESI, we're increasing what's referencing ESI. So this here is, it doesn't really know what it means to increase ESI. So here we're saying increase ESI by word pointer. So increase it by 2. And that will increase the address of ESI. So right now we're going to do this and we're going to see what happens. So I'm going to go ahead and clear and get my mouse. Press escape. There we go. Okay, so we're going to stop this. We're going to create an array. And the array, it doesn't matter what the name of the array is. The array that they did was size word, and they had it with and actually they didn't even have an array. They just had this is just a variable. So we'll call it var1. I want to be able to see. I want to make it smaller. It's just making it bigger. I want to see what they did. Okay, so then they said offset the variable, move it to ESI. Okay, so get the address of the variable. Okay, so we get the address of var1 and moved it to ESI. Then they increased ESI. And that's it. So that's the first thing. So the first thing we want to see is how this runs. So if we actually run this example, so many things in my way, making it hard to run. We get an error, and the error says instruction operand must have a size. So if I double click on this error, it shows me right here that I have to have a size to increase by. So I'm going to go ahead and do that. So I do that by doing word pointer ESI. So right here, I'm going to tell it what size. So I'm going to say, go ahead, and this is a word size pointer, increase it by 2. So now when I run it, I shouldn't get an error. So what I want to do is I want to set a break. I want to look at my ESI register. So we have var1, and when we have ESI. We want to look at the address of var1 and make sure that that address gets put into ESI. So we've set a breakpoint. We're going to run it. We're going to look at right here my variables. So this is the watch one, which watches my variables. I'm going to go ahead and delete it and add var1. Actually, I don't want to see var1. var1 has a 0. What I want to see is the address of var1. So address var1. So the address of var1 is 64000. I'm going to look at my registers. I'm going to look at ESI. And I'm going to step over. And ESI now has the address of var1. A64000. A64000. That's the address of var1. Okay. And then I'm going to step over and it's going to increase by 2 because a word is 2 bytes. And ooh. And here we go. So we've so actually it's increased by 1. So what it's doing, I was wrong. Okay, so we're dereferencing ESI. That means that we're not looking at the address, which I did say that earlier. We're not looking at the address, we're looking at the value, right? So since we're looking at the value, then we're not increasing the memory address like we were doing before. Now we're increasing the value in ESI of what, not in ESI, but the value that ESI points to. So ESI points to var1, which was a 0 earlier. And so if we increase what it points to, then increases 0 to 1. So because it's in brackets, we're actually increasing the value that it points to. So we're going to stop it and we're going to take the brackets off. Let's see what this does. See if it likes it. Nope, doesn't like it. Invalid use of register. So here we can't have a register. We can only have a variable, but we can offset it like this. So ESI points to var1, which holds a 0, and we're saying increase what this is pointing to, so it increases this to 1. Okay, hopefully that all makes sense. And so here it says, should pointer be used here? And the answer is yes, because ESI could point to a byte word or double. So to fix this, right in front of this bracket, we would put the size. So we put word pointer or double pointer or whatever the size it is. Okay, array sum example. So in this example, we're using indirect operands for traversing an array. Traversing means going through the array. Note that the register in brackets must be incremented by a value that matches the array type. Okay, so here the array is called array W. And it contains 1, 2, 3 elements. ESI now points to the array W. Here, we're dereferencing ESI. So this right here has the value 1000. 1000 H gets put into AX. And then we're adding 2 to ESI. or it says we can do type array W, add type array W. So here, what we're doing is adding 2 bytes to get to the next element. So we didn't add 1 because this is a word size array. Okay. Then here, we move the next value. So we move 2000 into AX. Actually, we're adding, so we're adding 2000 plus 1000. And then we move to the next value. So we're adding 2 to ESI. That means that you're adding 2 bytes to the address that array W, that ESI points to, which is array W. And then we dereference ESI, so we get to the 3000 and we add it to AX. And this gives us the sum of all 3 numbers. So let's see if I can show you. Okay, so let's say that this begins at FF 0, 0. I'm just going to write the 2 zeros just because it's so hard to write with this pencil. So this would be FF00, this would be FF02 because these are word size. This would be FF04. ESI is going to contain FF00. It's going to contain the address of where the first element lives. And then here we're saying, okay, give me what's in 0, 0. So because we have the brackets, it's dereferences. So the address is FF00, so it grabs what's in here and it puts it into AX. So now AX has 1000. Then we add 2 to ESI. So ESI is at FF00. FF00 plus 2 gets us to the 2000. That 2000 gets added to ESI. This is what gets added to the value of ESI, not. So remember, it doesn't have the brackets. If it doesn't have the brackets, it gives you the value. So it gives you this value 1000. So ESI, ESI contains 1000. But ESI with brackets means that it points to this address or whichever address. Okay. So here we're adding 2 to ESI, which is the address. Here we're referencing what's in that address, which is 2000, and we add it to AX, so 2000 plus 1000. And then here we get to here, and then we dereference, so we add 3000 plus the 3000 that we had added here. So go ahead and type this in, run it. What you want to do is you want to look at the AX and ESI and just see what values they get as each of these, as you step through each of these statements. All right, indexed operands. An index operand adds a constant to a register to generate an effective address. Effective address just means it gives you an address where a variable lives. Okay, so it gives you FFE0 or FFE2. And so you're just adding a constant. So you're saying like FFE0 plus 2 or FFE0 plus 5. So here we have array W. It has 1, 2, 3 elements, same array we had earlier. We moved 0 into ESI, and now we're adding 0 to the name of the array. So when you add 0 to the name of the array, you're adding 0 to the address. Array W contains the address of where 1,000 H lives. That's all it contains. It doesn't have the address of where 2,000 lives, and it doesn't have the address where 3,000 lives. It just has the address where 1,000 hexadecimal lives. So 0 plus that points to this location right here. Let me see if I can write. Okay. So array W, let's just pretend it is at FFE0. So I'm going to put E0 here. So this would be E0 plus 0 is E0. And then that gets us the 1,000, and it gets moved to AX. And then we have array W, ESI. So array W is FFE0. ESI is 0. So this is another way that we could do it. So this is like the C++ way, right? Or even Java where you put you have your array and then you have a 0 or a 1 or a 2 right here. So you could do it this way, or you could do it this way. And it's going to get you the same thing. It's going to get you to the 1,000. Now, if you add 2 to ESI, well, ESI is just a constant. ESI had a 0 in it. So if you add 2, now ESI has a 2, right? And so if you say array W, which at FFE0 plus 2 gives you to E2. This is where E2 lives right here. This is what E2 is pointing to, FFE2. And so it gets you the 2,000. So you have 2,000 added to 1,000. So AX would be 3,000 right here. 3,000 hexadecimal. Okay. Then here at the bottom, it just says to modify this example for an array of double words. So let's clear everything. If we had to modify this for double words, of course, we would put a D here, right? For double, put a D there. But because it's double words, it's no longer 2 bytes. These are 4 bytes each. Each element is 4 bytes. So this is 0, 0. This is 0, 4. And this would be at address 0, 8. Therefore, I start at 0, but I have to bump not by 2, but by 4. So I have to change this to a 4 to get to here. All right, so that's the end of that. Clear on that one. And then let's go back to the mouse. Index scaling. You can scale an indirect or indexed operand to the offset of an array element. This is done by multiplying the index by the array's type. Kind of did this a little bit before. So here we have, we're moving 4 into ESI. I'm going to get my pen again. Okay, so ESI has 4. Now I'm going to multiply 4 times the type of the array B. So array B is a byte. So this would be a 1 because the type, it gives you the how many bytes. So 4 times 1 is 4. So there would be a 4 here. So array B sub 4 would be, this is 0, 1, 2, 3, 4. So it gets you this number right there. This is ESI, which is still a 4. And we're going to multiply times the type of array W. Well, array W is a word, that's 2 bytes. So we multiply times 2. 4 times 2 is 8. Array W to get to the 8th byte, we're going to go 0, 2, 4, 6, 8. So it's going to give us this number. Because remember, we're going to skip count by 2s because this is size byte 2, starting always at 0. 0, 2, 4, 6, 8, 10. This is 1 byte. 0, 1, 2, 3, 4, 5. This is double. 0, 4, 8. 12, so on and so forth. Okay, so this last one, it's 4 times type array D, type array D. This is 4 bytes. So it'd be 4 times 4 is 16. So 0, 4, 8, 12, 16. 16 gets us to the 4 right here. So that's the value that gets moved into EDX. Notice too how they're writing it here. Because this is a byte, they write 0, 4. Because this is 2 bytes, they write 0, 0, 0, 4. Because this is 4 bytes, they write 1, 2, 3, 4, 5, 6, 7 zeros and a 4. So you need 2 digits per byte. So 1, 2, this is 1, 2, 3, 4 bytes. This is a double word, just 4 bytes. Okay. Clear all drawings. You can type this also, run it, and look at the registers and see that it gives you these values. Next. Pointers, you can declare a pointer variable that contains the offset of another variable. Remember, so you can declare a pointer variable that declares the address of another variable. That's what the word offset means. So here we have array W word. So this array contains these 3 elements, and this pointer here points to this array. So you just have you can get to this 1000 here by saying array W, or you can get to the 1000 by saying pointer W. Either one's going to get you to the same place. In this example, we're moving pointer W to ESI. So ESI now holds a pointer 2 to this array. And here we're dereferencing ESI, so it gives us the 1000. ESI points to the 1000. Pointer W points to the 1000. Array W points to 1000. So just another way of doing it. Here's an alternate format they're giving you that you could say pointer W, double word, offset. You can add the word offset right here. Array W. Okay, so that's the end of this video. Make sure that you run the examples, that you understand this fully, and then go into the last section that we're going to talk about, which is jump and loop instructions.